The night sky has always captivated humanity. Look up, you see tiny points of light. These are stars, suns like our own but very far away. Beyond them lies an expanse so vast it challenges our imagination. It is a realm of profound mystery and incredible beauty. We have only just begun to scratch the surface of its secrets. Every new discovery opens up even more questions. The universe is a grand cosmic tapestry, woven with phenomena that astound us. Our curiosity drives us to explore this immense unknown. We send probes into the void. We strive to understand our place within this cosmic ballet. What lies out there, beyond the reach of our unaided eyes? There are worlds stranger than we can dream. There are forces more powerful than we can comprehend. The scale of space is truly mind-boggling. It stretches in all directions, seemingly without end. This journey will delve into some of its most fascinating yet lesser-known wonders. Think about the sheer number of stars. Our own Milky Way galaxy contains hundreds of billions of them. And there are hundreds of billions, perhaps trillions of other galaxies in the observable universe. Each star could potentially have planets orbiting it. The possibilities for unique environments and strange phenomena are almost limitless. Deep space is not empty. It is filled with energy, matter, and events on an epic scale. It is a dynamic and ever-changing place. We are explorers by nature. The call of the unknown is strong. Understanding the universe helps us understand ourselves. It tells us about our origins and our potential future. The facts we will uncover are more than just trivia. They are pieces of a giant puzzle, a puzzle that reveals the fundamental laws governing everything. So let us embark on this voyage. Let us gaze into the depths and marvel at what we find. The cosmos awaits our attention and our wonder. Many people imagine space as completely silent and odorless. This is partly true, but also partly a misconception. Space is a near-perfect vacuum. Sound waves need a medium, like air or water, to travel. Since there is virtually no air in space, you cannot hear sounds in the traditional sense. An explosion might happen next to your spaceship, but you would not hear the boom. This profound silence is one of the defining characteristics of the void. It is a quiet, unlike anything on Earth. However, space is not entirely devoid of sensory information. Astronauts returning from spacewalks have reported distinct smells. When they re-enter their spacecraft and remove their helmets, their suits carry peculiar odors. Some describe it as the smell of burnt metal or welding fumes. Others have noted scents reminiscent of gunpowder, seared steak, or even raspberries and rum. These smells likely come from polycyclic aromatic hydrocarbons. These are compounds released by dying stars and found in cosmic dust. The source of these space smells is fascinating. They are the chemical signatures of cosmic processes. The burnt metal aroma might be from high-energy vibrations of particles, or perhaps from reactions with atomic oxygen clinging to the fabric of their spacesuits. The universe is constantly cooking up complex molecules. These molecules drift through space. They can stick to surfaces like astronaut suits or meteorites that fall to Earth. So, while you cannot hear in space, it seems you might be able to smell it indirectly. This idea challenges our typical perception of space as an empty, sterile environment. It is in fact a place filled with subtle chemical interactions. Radio waves, another form of information, travel perfectly well through the vacuum. This is how we communicate with satellites and probes. It is also how we receive signals from distant celestial objects. So, while your ears would find silence, other senses and instruments can pick up the whispers and even the aromas of the cosmos, painting a richer picture of its nature. Imagine a planet made almost entirely of diamond. This is not science fiction. Astronomers have found a planet named PSRJ 1719-1438b, which is likely a giant diamond. It orbits a rapidly spinning neutron star called a pulsar. This planet is thought to be the remnant of a once massive star. Its outer layers were stripped away by its companion pulsar. What remains is a core made mostly of carbon under immense pressure. Such conditions could crystallize the carbon into diamond. This diamond planet is about 5 times the diameter of Earth. Yet, it is much denser. It orbits its pulsar in just over 2 hours, at a very close distance. The universe is full of such exotic objects. Planets can form in ways we are only beginning to understand. Some are gas giants like Jupiter, others are rocky like Earth, and some, it seems, can be cosmic jewels of incredible size. This discovery shows how diverse planetary formation can be. Nature's imagination often surpasses our own. Beyond planets orbiting stars, there are also rogue planets. These are worlds that drift through space all alone. They do not orbit any star. They wander the cold, dark interstellar void. Scientists believe there could be billions or even trillions of these rogue planets in our Milky Way galaxy alone. Some may have been ejected from their original solar systems due to gravitational interactions. Others might have formed in isolation from smaller clouds of gas and dust. Detecting these lonely wanderers is very difficult. They do not shine with their own light. They do not orbit a star, so we cannot easily spot them using traditional planet-finding methods. However, techniques like gravitational micro-lensing offer a way. This occurs when a rogue planet passes in front of a distant star. Its gravity bends the starlight, causing a temporary brightening. These rogue worlds are fascinating. Could they harbor life in subsurface oceans warmed by geothermal activity? The universe keeps presenting us with such tantalizing possibilities. We can actually see a baby picture of the universe. This is known as the cosmic microwave background, or CMB. It is ancient light that has traveled for about 13.8 billion years to reach us. This light was released when the universe was only about 380,000 years old. Before that, the universe was a hot, dense soup of particles and radiation. Light could not travel freely. As the universe expanded and cooled, protons and electrons combined to form neutral atoms. This allowed light to escape and travel through space. The CMB appears as a faint glow of microwaves from all directions in the sky. It is remarkably uniform, but it has tiny temperature fluctuations. These fluctuations are incredibly important. They represent the seeds from which all cosmic structures like galaxies and galaxy clusters eventually formed. Studying the CMB gives us vital clues about the early universe. It tells us about its age, its composition, and its rate of expansion. It is like an archaeological dig into the very beginnings of time and space. Another fascinating and somewhat unsettling cosmic process is galactic cannibalism. Larger galaxies often grow by consuming smaller ones. Gravity is the culprit. It pulls galaxies together. When a large galaxy and a smaller dwarf galaxy approach each other, the larger galaxy's gravitational pull can tear the smaller one apart. Its stars, gas, and dust are then absorbed into the bigger galaxy. Our own Milky Way galaxy is currently in the process of eating several smaller dwarf galaxies, like the Sagittarius dwarf spheroidal galaxy. This process of galactic mergers is a fundamental part of how galaxies evolve. It is a violent yet creative force in the universe. Over billions of years, these mergers build up the massive spiral and elliptical galaxies we see today. In about 4.5 billion years, our Milky Way is predicted to collide and merge with its even larger neighbor, the Andromeda Galaxy. This future cosmic event will reshape our galactic neighborhood entirely. It is a reminder that the universe is a dynamic place, constantly changing on grand scales. Section 5: Celestial Titans, the unfathomable nature of black holes. Black holes are some of the most extreme and mysterious objects in the universe. Imagine a region of space where gravity is so strong that nothing can escape, not even light, the fastest thing in the universe. This is a black hole. They are typically formed when a very massive star, much larger than our sun, runs out of fuel. Its core collapses under its own immense gravity. This collapse is so complete that it creates an object of incredible density and an inescapable gravitational pull. At the heart of a black hole is something called a singularity. This is a point of theoretically infinite density, where our current laws of physics break down. We do not fully understand what happens at a singularity. Surrounding the singularity is the event horizon. This is the point of no return. Anything that crosses the event horizon, gas, dust, stars, light, is trapped forever. It is the boundary beyond which escape is impossible. Black holes are truly nature's ultimate traps. There are different sizes of black holes. Stellar mass black holes are a few times the mass of our sun. Then there are supermassive black holes. These giants reside at the centers of most large galaxies, including our own Milky Way. Sagittarius A*, the black hole at the center of our galaxy, has a mass of about 4 million suns. Some supermassive black holes can be billions of times the mass of the sun. How they grow so large is still an active area of research. Because black holes do not emit light themselves, they are invisible. So how do we find them? We detect them indirectly, by observing their effects on nearby matter and stars. Stars can be seen orbiting an apparently empty point in space. Gas and dust drawn towards a black hole form a swirling, superheated disk, called an accretion disk. This disk can become incredibly bright, emitting X-rays and other radiation. Sometimes, powerful jets of material are ejected from the vicinity of the black hole at near light speed. These are the telltale signs of these cosmic monsters. Section 6. Cosmic Beacons, the astonishing density of neutron stars. When a massive star dies in a supernova explosion, its core can collapse. If the core is not massive enough to form a black hole, it can become a neutron star. These are incredibly dense objects. Imagine squeezing more than the mass of our sun into a sphere only about 20 kilometers or 12 miles in diameter. That is like packing a star into the size of a city. A single teaspoonful of neutron star material would weigh billions of tons on Earth. This density is almost unimaginable. Neutron stars are made almost entirely of neutrons, packed tightly together. This is what gives them their name and their extreme density. They are born spinning very rapidly, a consequence of the conservation of angular momentum from the original star's collapse. Some can rotate hundreds of times per second. Their magnetic fields are also incredibly strong, trillions of times stronger than Earth's magnetic field. These extreme properties make neutron stars fascinating laboratories for studying physics under conditions impossible to replicate on Earth. Some neutron stars, known as pulsars, emit beams of radiation from their magnetic poles. These beams are usually radio waves but can also include visible light, X-rays and gamma rays. As the neutron star spins, these beams sweep through space like the beam of a lighthouse. If one of these beams happens to sweep across Earth, our telescopes detect a regular pulse of radiation. This is why they are called pulsars, for pulsating radio sources. They were first discovered in 1967 and initially puzzled astronomers. Then there are magnetars. These are a special type of neutron star with even more extreme magnetic fields. Their magnetic fields are 1,000 times stronger than those of ordinary neutron stars. That is quadrillions of times stronger than Earth's field. These ultra-strong magnetic fields can cause starquakes on the neutron star's surface. These events can release enormous bursts of high-energy X-rays and gamma rays. Magnetars are rare, but they are some of the most magnetic objects known in the universe. Section 7. Worlds Unnumbered. The search for exoplanets beyond our sun. For centuries, humans have wondered if other stars have planets like our sun does. We now know the answer is a resounding yes. Planets orbiting stars outside our solar system are called exoplanets. The first confirmed exoplanets were discovered in the early 1990s. Since then, thousands have been found, and the number is constantly growing. Astronomers estimate that there are billions, perhaps even trillions of exoplanets in our Milky Way galaxy alone. It seems that planets are a common byproduct of star formation. Scientists use several clever methods to find these distant worlds. One common technique is the transit method. If an exoplanet's orbit is aligned just right, it will pass in front of its host star from our point of view. This causes a tiny temporary dip in the star's brightness, which our telescopes can detect. Another method is the radial velocity or wobble method. A planet's gravity tugs on its star, causing the star to wobble slightly. We can detect this wobble by observing shifts in the star's light. Exoplanets come in a stunning variety of sizes and types. There are hot Jupiters, which are massive gas giants orbiting very close to their stars, with scorching temperatures. There are super-Earths, which are rocky planets larger than Earth, but smaller than Neptune. Some exoplanets orbit two stars, like Tatooine from Star Wars. Others might be water worlds, completely covered by deep oceans. Scientists are particularly interested in finding exoplanets in the habitable zone of their stars. This is the region where temperatures could allow liquid water to exist on the surface. The ultimate goal of exoplanet research is to find signs of life beyond Earth. This is one of the most profound questions in science. New powerful telescopes, like the James Webb Space Telescope, are designed to study the atmospheres of exoplanets. By analyzing the starlight that passes through an exoplanet's atmosphere, scientists can look for biosignatures. These are gases like oxygen or methane that could indicate the presence of life. The search for other Earths and potentially other life is an exciting frontier. Section 8. Universal hydration and colossal structures, water and cosmic walls. When we think of water, we usually think of Earth's oceans, rivers, and lakes, but water, H2O, is actually one of the most abundant molecules in the universe. It is not just confined to our planet. Water ice is found on comets and asteroids within our own solar system. It is present on moons like Jupiter's Europa and Saturn's Enceladus, possibly in vast subsurface oceans. Water vapor has even been detected in the atmospheres of some exoplanets orbiting distant stars. The sheer amount of water in the universe is astounding. Astronomers have discovered a colossal cloud of water vapor in a quasar located over 12 billion light-years away. This cloud contains an estimated 140 trillion times the amount of water in all of Earth's oceans. It is the largest and most distant reservoir of water ever detected. This tells us that the conditions for water to form were present even in the early universe. Water is a fundamental ingredient, scattered far and wide across the cosmos. Beyond individual planets and molecules, the universe also contains structures of truly mind-boggling scale. Galaxies themselves are vast collections of stars, but galaxies are not distributed randomly. They are often found in groups called galaxy clusters. These clusters, in turn, can be part of even larger structures called superclusters. One of the largest known structures in the universe is the Hercules Corona Borealis Great Wall. It is a colossal filament of galaxies, stretching about 10 billion light-years across. To put that into perspective, the observable universe is about 93 billion light-years in diameter. So, this single structure spans more than 1/10 of that distance. Its existence challenges some of our cosmological models. According to the cosmological principle, the universe should be roughly uniform on very large scales. Structures this enormous suggest there might be aspects of cosmic evolution we do not yet fully grasp. Discovering such immense formations pushes the boundaries of our understanding of how the universe is put together. Section 9. The universe's true-scale stardust, slow light, and endless wonder. We often hear that the speed of light is the ultimate speed limit in the universe. It travels at about 299,792 kilometers per second, or about 186,282 miles per second. This seems incredibly fast by human standards. However, when we consider the vast distances of space, the speed of light suddenly seems quite slow. Light from our sun takes about 8 minutes and 20 seconds to reach Earth. If the sun were to suddenly disappear, we would not know about it for over 8 minutes. Light from the nearest star system to ours, Alpha Centauri, takes over 4 years to reach us. To cross our own Milky Way galaxy, light takes about 100,000 years. And the light we see from the most distant galaxies has been traveling for billions of years. This means that when we look at distant objects, we are actually looking back in time. The finite speed of light acts as a cosmic time machine. It allows us to see the universe as it was in the distant past, providing a window into its history. Another profound cosmic fact is that we are made of stardust. The very atoms that make up our bodies, the Earth, and everything around us were forged in the hearts of stars. The early universe was mostly hydrogen and helium. Heavier elements like carbon, oxygen, nitrogen, and iron, essential for life as we know it, were created inside stars through nuclear fusion. When massive stars reach the end of their lives, they often explode as supernovae. These explosions scatter these newly formed heavy elements across space. This enriched material then becomes part of new clouds of gas and dust. These clouds, in turn, collapse to form new stars and planetary systems, including our own Sun and Earth. So the calcium in our bones, the iron in our blood, and the carbon in our DNA were all cooked in stellar furnaces billions of years ago. We are, quite literally, children of the stars. This connection to the cosmos is both humbling and inspiring. It links us directly to the grand cycle of cosmic birth, life, and death. The universe is a place of unending wonder. Its scale is almost beyond human comprehension. Every discovery seems to reveal even deeper mysteries and more intricate beauty. From the silent, scented void to diamond planets and lonely wanderers, from galactic feasts to the echoes of creation itself, space is a realm of constant surprise. The quest to understand the cosmos is a journey without end. It stretches our minds, fuels our curiosity, and ultimately helps us appreciate our own precious existence on this small blue planet. The universe is not just out there, we are part of it, and it is part of us.